Hello, today we're going to be talking about stuff in Catboy gravity. So we're going back to Catboy gravity. And yeah, I'm sorry I have to keep switching or saying in the beginning of these lectures whether on their what course they're record under because we keep switching between courses. So today we're going to be talking more on the Schwarszchild metric. So the Schwarszchild metric. And some additional stuff about the Reisner-Nordstrom metric. Uh, so, concerning Reisner-Nordstrom, I need to correct myself on that one footnote that I did about the Reisner-Nordstrom metric. And I need to state first that the Reisner-Nordstrom metric is actually not a vacuum solution. So recall that vacuum solutions are basically solutions such that T mu nu is set to 0. So the left hand side is rather trivial. It would be just so my Einstein field equations would just be R mu nu minus lambda G mu nu equals 0, where R mu nu is another tensor that's derived from G mu nu and a bunch of Christoffel symbols, and lambda is my constant, or something like that. But the thing is, the Reisner-Nordstrom is actually a solution for when T mu nu is not 0. In fact, it's actually something. So I want to discuss first about electric fields. So let's talk about electric fields a little bit. And one neat thing about general relativity is that from the complex machinery of differential geometry and the like, we can actually rederive or actually come back to trivial stuff, such as, I mean, not really trivial, but rather some fundamental things, such as Maxwell's equations. So so first, let's consider electric currents. So I'm assuming you guys know about four velocity already. So I'm going to be using four velocity notation. So a current J vector is a 4 vector consisting of the charge density rho and a 3 vector. So this is denoting my space-time vectors here. It's actually a vector field. So this actually, so rho is observed. So whenever I cite a quantity such as, like, say, a 3 vector v, so v, not nu's like this, but talking about v, a 3 vector, I'm saying it, or I'm stating it as it is observed by an observer. So really, these things will be related via a Lorentz transform. So for those saying, oh, how about a different rest frame, right? What if I have a different observer and I try to observe rho or these quantities? Of course, since these guys are space-time 4 vectors, there is always a Lorentz transform that relates the two. Okay, so if I have one femboy observing a phenomenon here and then another one here, then of course their observations, or rather the quantities associated with them, or the quantities we use that we observe using them, will be, or actually their measurements will be related via a Lorentz transform. So I want to get that out of the way. So recalling that, notice that almost every quantity in physics that we know is conserved. So energy is conserved. Of course, there's the second law of thermodynamics. There's also momentum. Momentum is also conserved depending on the type of collision you're considering. It's completely conserved in inelastic collisions, of course, physics 101. And of course, charge will be conserved as well. So recall that the rate of change of my charge density with respect to time is actually minus the 3 Laplacian times j. So you can interpret this here as maybe my d over dx, d over dy, d over dz. But of course, in the end of the day, we're still also considering z, x, and y as functions of my proper time tau. So in the end, you're going to have to take care of a factor dx by d tau, dy by d tau, and dz by d tau, right? So yeah. And I can shorten this notation into its components, which is del alpha, j alpha, and that's equal to 0 because of course it's conserved. Now, let's consider now electric fields as we remember them from physics are composed of 3 components, or actually they're composed of 2 fields that contains 3 components, of course. So the field is the electricity part, so electric charge, and of course there's the other one that's magnetic charge. So it's not just, of course, electric currents are electromagnetic. So because they have 2 different fields in them, and each of these fields have 3 components that we require to describe them, we essentially need a tensor, right? Remember that tensors take in vectors and then gives us Lorentz invariant scalars. We need tensors, or we need a tensor that gives me rather 6, or rather that has to account for those 6 components. So now let's hypothesize a tensor, a 4x4 tensor, so such that 4 is on the diagonal and 6 is off diagonal. So a 4x4 tensor, of course, contains 16 components. So I'm going to call my hypothetical tensor f mu nu, and I'll start with f00, and then this goes to f 4, and then this goes to f no, actually this is f 40, and then this goes to f 04, and these guys go to 4. So these have 16 components, but we really only need 6 functions to describe the fields of my electric current. So 16 components, that's too much to describe 6 components for my electric field. So what we now want to do is consider an anti-symmetric tensor. So my I'm going to require that my fm mu nu is actually such that f mu nu is equal to minus f mu nu. Okay, so what do I mean by it satisfying this over here? So that means that diagonals will only be the case here. So when I combine them together, when I add them together, they become 0. So of course, transposing this to the other side tells me that f mu nu plus f mu nu is equal to 0. And so this only works when only the diagonals, or actually some components of it, are there. So it only works for certain cases. Or actually, it only works when the diagonals are all 0. So when we force this requirement, of course, the diagonals are 0, and only 6 of diagonal components are left. And so we now have a new tensor, which is f mu nu, which is of the components 0, ex, ey, ez, not 2, z, minus ex, minus ey, minus ez, and then the diagonals are 0. So the next entry in the second row is 0, and then this is bz minus by minus bz minus by, no, just by, by, and then that's 0 bx, bx, and then this is 0. And this is sufficient. This is enough to describe what exactly our electric field is. And in fact, when we try to take its derivative with respect to the new components, so d nu, so recall that I'm just gonna write it down here. D nu is basically d by dx nu. Okay, so d nu of f mu nu is equal to 4 pi j mu. So the mu component of j. And then d mu f mu lambda plus d mu f lambda mu plus one more component plus d mu f mu nu is equal to 0. And what we're doing is just lowering the indices down, I believe by using my Levi-Civita symbols or some other factor. If you guys can point that out, I would appreciate it. Okay, and you'll find that actually if you do this, you will get Maxwell's equations. This gives us Maxwell's equations. Okay, so as for that, and what my point is right now is that this f mu nu is a component of my stress tensor, right? The thing is, this is non-zero because the Reiser-Nordstrom metric it takes into account a charged black hole that isn't spinning. So I have a catboy that is spinning, that's not spinning, but is charged, right? So that means there is a charge associated to it. There is an electric field that is induced by that charge, and therefore my F mu nu and thus my T mu nu is non-zero. So I was wrong when I said that it was a vacuum solution. It's actually not a vacuum solution. So there's that. Now, as for the Schwarzschild metric, I want to state another way of expressing the Schwarzschild metric, and that's in Cartesian coordinates. If you guys would see in the Wikipedia, it's actually called isotropic coordinates. So there's some additional caveats I'm kind of skipping on right here, but this is essentially the thing of it. So this is my line element. The s squared is minus 1 minus rs over 4r, big R, squared over 1 plus rs over 4r squared dt squared plus 1 plus rs over 4r to the fourth, and then this is just dx squared plus dy squared plus dz squared. You guys can call that like eta mu nu, like the three components of eta mu nu, or the line element of eta mu nu. So like eta mu nu, dx mu, dx nu, but the entire thing like only considering components in the 3 dimensions, not the time dimension, because the time dimension is already factored in. And you may be wondering, where's the c in this case? Because originally my Minkowski metric actually is mu nu. So my line element mu nu dx nu is minus c squared dt squared plus, well, dx squared plus dy squared plus dz squared. So you may be wondering, how come here in this formulation c is not present? Well, let's talk a little bit about units. So the thing is, to make computations so you guys make much easier, usually when you take your first introductory course in general relativity, especially the lectures done at MIT, we actually set c equal to 1. And it's not as paradoxical as you think. We're not doing any trickery here or magic. The units are still there, right? But the thing is, what we want to do is try to formulate c or talk about c in a way that makes our calculations much more convenient. So what we're talking about is essentially setting c, so we're standardizing basically to light units. So we're saying c is 1 light time unit over time unit, so at a certain time unit. So you could talk about it like 1 over 2 seconds or something like that, but what we're essentially doing is standardizing, and time units and then just like stuff like that cancels out and just gives us 1. Right? So if my time unit is 1 second, the length unit is 1 light second. If it's 1 light nanosecond, then my time unit will be 1 nanosecond. And surprisingly enough, I know this is kind of disgusting considering for us metric system users, but 1 light nanosecond is actually approximately equal to 1 foot, right? I mean, because of course multiplying c by a time unit gives me, of course, a length, right, or a distance. So, funnily enough, 1 light second or light nanosecond. So multiply the speed of light by 1 nanosecond, and I actually get something that's approximately equal to, within 2 millimeters of a precision, 1 foot. It's crazy, but that's physics for you. We make the most seemingly unrelated connections, and also math, of course. So there's that. So that's why in certain instances we set c equal to 1, and in the end we have that, of course, dt squared minus dt squared plus dx squared plus dy squared plus dz squared is my line element. And sometimes from here on out I will omit c and just say it's just 1, right? And you won't see c much, but we still keep in mind this sort of formulation in the end. All right, so this is it. And r of course is the radius of my body, so my Catboys world sphere. And I never justified why I call it the world sphere. So of course when we're talking about geodesics or trajectories through space-time, we're of course considering like Catboys or whatever you guys want to think of them, are traveling through space. Think of them as a point particle, and the trajectory they trace out through space-time, which evolves through time, right? So not just through space, of course, it changes directions and stuff like that, but it warps depending on time. If it's a constant sort of trajectory, then it stays the same through time. If let's say I have a bottle, I put it on my desk and I let it be, it's still traveling, just temporally speaking. It's traveling through time, but not through space. All right. But the point is, what I'm saying is that these trajectories, which we call, of course, the world lines, well, these things are what we trace out, what the trajectories trace out, or what these particles or these people trace out as they travel through space-time. Now here, for the world sphere, what we're doing is revolving or thinking of course, we have the height of our given Catboy, and then we revolve it through all the axes. So all the x, y, and z axis or if you guys want to think about it, the r, theta, and phi axis, if you want to think in polar coordinates. We're revolving it through space. We're having it travel through space, but it's constant in time. So technically, we can think of it as something that's analogous to a world line or a world sheet if you're talking about string theory, but we're just talking about basically as a construct, an object, right? So that's why I call it a world sphere, because we're talking about a sphere, right? And of course, we're working in 3 dimensions of space-time, not just 2. All right. So that's why I call it a world sphere. I never seemed to justify that back when we started this series, or when we started this course. All right. So let's talk about wormholes. So you guys know about wormholes. It's a very common thing in science fiction, wherein what we do is basically fold, quote unquote, fold space, and then poke a hole through it, such that when I travel through the hole, I essentially get to the other side of the galaxy with no time at all wasted, right? So without an excessive amount of time. So basically, my proper time as I travel through this wormhole is minimized. So as opposed from, let's say that this is space-time, it's a sheet of paper, I will travel on a trajectory across it from some point A, I'll use a color for this one, some point A to another point B, right? And it's gonna take me some proper time, so some S, right? Which is just the integral of, the integral of this, the integral of the square root of my eta mu nu dx nu, basically. So it's my proper time. So between 2 certain seconds, right, I'm gonna know, from this is t0, it starts at t0, ends at t1. So my t0 to t1, or rather tau actually, because we're talking about clock on my ship. So we're talking about the clock on my ship as I travel through space-time, so we're talking about proper time, not really just the time in a different observer's rest frame or frame of reference. So this is from like a tau 1 to a tau 2, right? That's my time traveled. But the thing is, when we're talking about light years, right? Because of course space, length in space are either described via astronomical units, which is the distance from the Earth to the Sun, or 1 light year, which is what's the distance a light beam travels in 1 year. And these are very large distances. They are trillions of kilometers long or billions of miles long. And of course, I don't want to travel that long, because when I try to travel that long, even with our fastest, you've heard this narrative already, even though I go as fast as I could with our known propulsion technologies, it would still take me like 1,000,000 years to complete even just 1 light year to travel. So if the distance between these points A and B are very large in terms of light year scales, of course it's going to take me a lot of time, right? My proper time, or the time it takes to travel, my S is going to be very big, and I want to get there in no time at all. I want my S to be minimized. And in order to do this, of course, we fold space-time. Now, I can't do this in real life because you guys can't see me, but we're folding space-time, if you guys can see my diagram properly. And then this is my point A, and this is my point B. What we're doing is taking a shortcut, so a shortcut through space-time. We're connecting those 2 points. So that's the essence of a wormhole, right? As you heard from all the narratives on popular science nowadays. But we're now going to get into the nitty-gritty of what exactly a wormhole is in terms of a metric. So, what exactly gives me a wormhole? Alright. So, a wormhole, also known as an Einstein-Rosen Bridge, if you guys will check in the Wikipedia, I don't recommend checking the Wikipedia, but it says in the Wikipedia it's a topological feature of space-time. And when you guys crunch the numbers, I suggest you guys do it as homework. or as part of exercise to crunch the numbers after we're done discussing about this. Crunch the proper time it takes to travel between like a sample wormhole. Like plug in an appropriate value for your Schwarzschild radius, right? But all right, what we're gonna do is take my Schwarzschild metric. We're gonna start with the Schwarzschild metric. So the Einstein-Rosen bridge. Sounds cool, doesn't it? Einstein-Rosen bridge. So before I get into it, I want to state first that this is actually not traversable. This is one of the non-traversable wormholes out there, but the principle stays the same. You could theoretically go into it and then come out the other end of the galaxy. The point is, we're connecting 2 points in space-time. And minimizing, of course, the theoretical proper time it takes to, or actually, proper time interval it takes to travel between point A and point B using these bridges. Well, quote-unquote bridges. So my Einstein-Rosen bridge is given by a substitution in my Schwarzschild metric. So start with the Schwarzschild, Schwarzschild metric. Okay. So what's the substitution we're gonna make? Well, we're gonna set u squared. So if you guys have taken general relativity, don't confuse this u with the 3 velocity u tilde. Okay, this is a different variable. All right. So I'm gonna set u squared equals to r minus 2m, where m, of course, is the mass of my Catboys world sphere, and dr equals 2u du. Okay. So 2m here, so it makes sense because when I take the differential of both sides, my 2m is a constant. It's gonna cancel out this r is gonna become dr, and then my u squared becomes u 2u du. Okay, so that makes sense. The substitution makes sense. When we make this substitution, so u squared is, so r, so another suitable thing, r is u squared plus 2m. Okay, so all right. So when I make this substitution in my Schwarzschild metric, so let's recall the Schwarzschild metric, my line element at least. So now we're working in polar coordinates, just so you guys know. We're not working in Cartesian coordinates because I think that's going to make things a bit hard. So my ds squared. So what I'm trying to do with deriving the Einstein-Rosen bridge is we're trying to find a metric for it, all right? So just to clarify that out, and I'm sure that's obvious. So it's minus 1 minus rs over r dt squared plus 1 minus rs over r to the minus 1 dr squared plus r squared times d omega squared. Or of course, d omega squared is the usual metric on the 2 sphere, as I mentioned many times already before. But I'll put it here just for your reference. D omega squared is d theta squared plus sine squared theta d phi squared. Okay, the standard metric on the unit 2 sphere. Okay, so when I make these substitutions, I would get, let's see if I can do this right, minus 1 minus rs over u squared plus 2m dt squared plus 1 minus 1 minus rs over the same thing, u squared plus 2m to the minus 1. And then I have my dr squared, which is 4 u 4u squared du squared. And then plus, well, r now is u squared plus 2m. So u squared plus 2m squared d omega squared. So I believe there are some simplifications you guys can do with this one. I would expand this out. So this would be 1 minus this. So that's a 1 over 1. And then I multiply, cross multiply, of course. So this is u squared plus 2m minus rs over u squared plus 2m dt squared plus, and the reason why I'm expanding this out because there's some suitable cancellation I believe I can do, but I don't think it's necessary in the end, over u squared plus 2m to the minus 1. And then this is 4u squared du squared plus u squared plus 2m squared d omega squared. So what I was essentially doing is I'm modifying my catboy of mass m in a way wherein you somehow like collapses, I believe, into a form of matter which bends space-time to the point wherein it punches a hole, well, quote-unquote hole, and then the hole sort of connects two distant points in space-time. So there's a really good description I saw on a MathStacks Exchange website on wormholes about why exactly we do this substitution. And let me just look that up real quick. So why exactly does the wormhole have this metric? So there's actually some just give me a moment. I think I got the wrong one. Alright, so there's actually, before this loads up, before that website loads up, let's get into another formulation for this metric. So or another formulation. So another way that people expressed it is by ds squared is equal to u squared times u squared plus 2m to the minus 1 dt squared minus 4 times u squared plus 2m du squared minus u squared plus 2m squared d omega squared. And I want you guys to verify that this one is equivalent to, of course, my original one making the appropriate substitutions. So some additional features of a wormhole spacetime is that it's free of singularities. So while my Schwarzschild has singularities for certain values of Rs and R, here we can't get any singularities, right? So another thing we can do, or we consider, is that this is actually not a vacuum solution, and there's yet another formulation that involves the speed of light, c, not equal to 1, surprisingly. So here's from Albert Einstein himself and N. Rosen, the particle problem in the general theory of relativity. The four-dimensional space is described mathematically by two congruent parts, or quote-unquote sheets, corresponding to u greater than 0 and u less than 0, which are joined by a hyperplane r equals 2m, or u equals 0, in which g vanishes. We call such a connection between the two sheets a bridge. So here's my first spacetime, and then here's my second spacetime, and then the bridge that they're talking about is this hyperplane that goes like that. So in no time, as we travel through that hyperplane, we get to where we need to in such little s. All right. So another thing for the Schwarzschild metric is that there is a formulation that involves electric charges. So if I can get this to load right. Yeah, can't do this. So I just urge you guys to search that up. But there is also a solution, or a version of my Einstein Rosen Bridge metric, that accounts for electric charges. All right. So so last thing for this lecture before we end is basically like another way of stating these metrics, such as the Kerr metric, and of course the Reisner-Nordstrom metric, and of course my Schwarzschild metric. So originally the Kerr metric itself and the Kerr-Newman metric are actually really freaking long, right? But we can actually express it in a much more compact way. So I'm gonna say my G mu nu is equal to my Minkowski metric, my Minkowski metric. I keep saying Minkowski metric, it's a Russian name. My eta mu nu plus f times these two component vectors, k mu, k nu. And of course, this is of course noting some vector matrix product, or a dot product between these things. So first thing, f. So this is for the Kerr metric. F is 2gm r cubed over r to the fourth plus a squared z squared. And somehow we're working with a modified form of, or a hybrid form of, a Cartesian and polar coordinate system, because we have both an r and z here. so that's z squared, and my k, so this is originally in boldface, so I'm gonna write in boldface because I can. K is r x plus ay over r squared plus a squared. And then the next component is ry minus ax over r squared plus a squared, and then 2 over r. And of course my mu nu for k and nu ranges from 0 to 3, 1 to 3, because my time component is already given by the Minkowski metric at the beginning. So mu and nu ranges from 1, 2, 3, and 3. Or of course these guys correspond to the 3 spatial directions x, y, and z. It's important to state that out. Alright. And of course we're also considering charge here. So when we consider charge and say that F is equal to g r squared over r to the 4th plus a squared sigma squared times 2mr minus q squared. For q, the charge, my metric becomes the Kerr-Newman metric. So g mu nu becomes the Kerr-Newman metric. Alright. And these variables r, x, and y are related in the same way I discussed them when I discussed about these metrics. I'm just stating a much more compact way of expressing them in terms of the Minkowski metric. And yeah, I don't know if I stated this, that these guys are related by oblate spheroid coordinates, of course. So in the limit when a approaches 0, my r actually approaches the real radius of my world sphere. So now I'm just gonna write it in square. R squared equals x squared plus y squared plus z squared. I didn't mention this. And so there's that. Some additional stuff. So I'll keep you guys posted whenever there are more metrics that we can talk about. That's also interesting. Now the thing with the Einstein Rosen Bridge is the thing is, all right, we're talking about physics. We have to talk about applications to reality. And the thing is, it's kind of impossible to travel through these things because the way we have to keep them open, the thing is, when we do have a wormhole, they're either very small, right? I mean, they sort of exist. They're hypothesized to exist in very, very small quantities, like very, very small scales. So what we want to do, right, is to widen them enough so that we can travel through them. The problem is we need exotic matter to do that. And exotic matter contains negative energy density. And there's no such thing as a negative energy density nowadays, or at least as we know with our current models, especially, of course, when I try to calculate the energy density of a certain, say, container of water, you guys probably know how to do that. It's chemistry, basic chemistry. You'll never come up with a negative energy density. There's no way in heck that's gonna happen, right? So that's what we call exotic matter. It has negative energy density, and it's sort of impossible, or at least it's almost impossible, near impossible to actually create them. So the way we hold these wormholes open is gonna be very difficult. And this metric assumes a space-time we cannot travel through. We can't travel through this wormhole. So if you guys think that this metric is gonna help us, actually get through interstellar distances, I'm sorry to dash your hopes. It's just impossible with our current knowledge. Same thing with the Alcubierre metric. I can talk about that, but we'll discuss about that in a different way. In the Alcubierre metric, what we're essentially doing is turning our catboy into a spaceship, rather. So we're misusing our astronomical catboy, our astronomy, astronomical catboy into a spaceship. We're misusing them. I mean, well, you could create like some very not symmetric metrics that can sort of induce propulsion on a spaceship near our astronomical catboy, or that astronomical catboy is just very impractical compared to chemical rockets, and of course, ion propulsion. So this is good for theory, for talking about theoretical physics. I mean, that is what we're doing right now, discussing theoretical physics. But application is just extremely hard at the moment, or near impossible. But I won't say impossible because there is some hope with regards to these things. I mean, here we require exotic mass. In the Alcubierre metric, we also need negative mass to even warp the space-time. So, or to create that bubble to warp space-time, right? So these kind of catboys cannot exist in real life, or these theoretical world spheres of catboys cannot exist yet. I don't want to say definitively if they will or will not exist, because we could beat the odds and then somehow force such a similar thing to happen in real life. So that's it for this lecture, and I'll see you guys in the next one.